In this podcast, we're going to start looking at the main event of stellar evolution, how stars evolve. We'll just start off by introducing the real basics. There's only really one variable that counts when it comes to the evolution of a star, and that is its mass. All stars start in the same way, in the stellar nursery, but from that point on, their lifetime and their eventual fate is determined purely by the mass of the resulting star. As I said, all stars come from more or less the same place. All stars being born today were first formed inside a giant molecular cloud. This molecular cloud may include primordial hydrogen and helium left over from the Big Bang, but most of its contents will be recycled from earlier generations of stars. So although it will mostly contain hydrogen and helium, there will also be a seasoning of other elements present. These giant molecular clouds are, well, big. They have a diameter of up to 100 light years and a mass of up to 6 million times the mass of our Sun. The closest one to us is the Orion Nebula at about 1,300 light years. There are some small, closer star region formations, but that's the nearest really big one. Within giant molecular clouds, star formation seems to take place in these Bok globules. These are relatively isolated and small dark nebulae with a diameter of about 1 light year and a mass of about 2 to 50 times the mass of our Sun. And if we look closely at some of these, we see the first protostars. Young stellar objects refers to any kind of object which is going to be a star but doesn't yet have that designation. On the left picture here, we have a protostar. The protostar is actually the one sort of near the top of the picture, about here. The protostar is starting to glow. The molecular cloud, the Bok globule, etc., has started to collapse, and that has created heat. So it's glowing from the heat of its creation. However, it's not finished the process, and although we can observe it because it is glowing, it's still adding more mass from the surrounding material. It's still getting bigger and more massive. A pre-main sequence star moves away from the protostar stage because it has actually now gathered all of the material and it has attained its final mass. But hydrogen fusion has not yet begun. The middle of that cloud of material is still collapsing. On the picture here, on the right hand side, we can see some very small items of nebula. These are only, the entire picture is only about 0.1, 0.15 light years across. So there's 5 different protostars visible here, and some of them are surrounded by disks that may well become disks of planets. Pre-main sequence stars are of 2 types depending on their mass. If it's less than 2 solar masses, they're known as T2.4a stars. Between 2 and 8, they are the much rarer Herbig A or B type stars. A star is born when nuclear fusion begins. And the first form of nuclear fusion that always occurs, because it's the easiest and takes the smallest temperatures, is hydrogen burning to helium through the proton-proton cycle. That creates energy. That energy is transmitted to the rest of the star, and the hot plasma that forms the star starts to provide some significant pressure. The core collapse, which has been starting to probably lessen off as due to the heat of the core, now stops. And the star assumes its shape, its mostly spherical shape, with gravity counteracting against the gas pressure which is pushing out. This is a state known as hydrostatic equilibrium. Hydrostatic equilibrium applies to all objects and fluids where you have two opposing forces. Now, the, um, the gas pressure that is created depends on the mass. The greater the mass, the greater the squeezing, the greater the heating, the greater the gas pressure. And this means we have different classes of these main sequence stars. We're familiar with these classes from earlier in the course, but we'll show this slide again. So the energy released gives faster burning of hydrogen. Greater core pressure means faster burning of hydrogen. Faster burning of hydrogen means a greater energy release per unit time, which leads to a hotter envelope and therefore to a larger star. So greater mass means larger, not just because the mass itself is greater, but just also because the rate of hydrogen consumption. Within the main sequence, the luminosity is not therefore linearly related to mass, but it's actually to the mass to the power of 3.5, as we have already discussed. So the main sequence is the adult life of a star, but how long it spends as an adult, as a hydrogen burning, depends very, very much on its mass, because it's the larger stars burn through their energy, burn through their fuel a lot quicker. M class, the faintest and smallest main sequence stars, can last for trillions of years, whereas the huge O class stars maybe only a few billion years, if that. However, there's not enough time in this presentation to look in detail at what happens next. So the next couple of presentations will take certain classes of stars and we'll look at those. So we're going to start with the low mass stars, sort of M, K, G, maybe F, and then we'll have another presentation on the high mass stars and the short but exciting lives that they lead. Okay, thank you very much.